Unfortunately, you can't just take any three notes and bang them together and expect it to be a chord. At least not in not before these postmodern times. What you see here is the infamous C, D flat, D chord. Taking the C, the D flat, and the D and banging them together. This is basically what happens if I try to play music. And so I will now demonstrate exactly what this sounds like. In mathematics, I can't even synthesize it. It sounds so bad. Now notice the wave pattern here is much longer pattern. Okay? Compared to the ones we saw here where the pattern was pretty short, here I've got a pattern that's much, much, much longer, and it doesn't sound so hot when you play it. One more thing along these lines. You put a few chords together, you get nice music. Anybody recognize this? Give you a hint, John Travolta. Yeah. This is Magic Changes from Greece. Okay? What genre of music does this remind you of? It's the same four chords being played over and over and over and over again. A C, an A minor, an F, and a D7, over and over and over again. This is the song Magic Changes from Greece. This is when John Travolta and Olivia Newton-John are dancing at the dance-off. This is playing in the background. It's actually part of the soundtrack for the Broadway play. When I taught this in pre-cal, I actually would give a demonstration of the song, but I'm not going to flip that on you guys. Yep.
Is there any such thing as a perfect chord with like a perfect period where it repeats perfectly?
I'm told there's such a thing as Pythagorean tuning on some synthesizers where they try to do exactly that, and
it only works for certain notes.
It only works for certain notes. Some notes sound weird as a result. Is that I mean, you might know more about this than I do. But it works for some notes, but some notes just sound weird because of it. So the answer is yes, it exists, but it doesn't quite work because you're trying to force something to be equal that isn't actually equal.
What was it called?
Pythagorean tuning?
Mm-hmm. It's like fourths and fifths work with that, but all the other ones sound wrong.
Yep.
Oh, right. Well then, yeah, there's another style of tuning, I think. I don't know. I think that there's a lot of different tuning systems. I think some of them work better than others. I don't know.
Okay, that's the limit of my knowledge. All right, here we have 440 hertz being added to 441 hertz. Okay, so I've got A above middle C at 440 hertz, and I'm pretending that there's a note on the keyboard at 441 hertz. And there's the graph of the function. Looks ugly, right? Sounds ugly, too. So here's what it sounds like.
That's pretty cool. It sounds like a tornado alarm.
That's right. Okay. Basically, a typical alarm clock. Why is this happening? Well, let's see. So that's the full graph. If I graphed it not over milliseconds, but over seconds, you can see it actually tuning in and tuning out going as time progresses. You can hear it going loud and soft as it plays. Okay, why is this happening? Well, there's a trig identity that makes this work. One of those trig identities we make our students memorize, and they forget it the second they learn it. And they actually forget it the second they have the test on it, they'll have to remember it again. And the trig identity involves sine of alpha plus beta. Or excuse me, sine of alpha plus sine of beta. Okay? Sine of alpha plus sine of beta can be represented as a product of two trig functions. And so the product, if you actually use the identity, it goes like this. You take the two angles and add them, you get sine, or average them, you get 881 pi times t. And then you also have a cosine term by taking the difference of those two angles and dividing by 2, which works out to be pi t. Okay? So what effectively happens is that the amplitude is now a cosine function itself. Rather than having a constant times the sine function, I have a cosine term times the sine function. So the term in blue there is determining the period, going loud and soft, and the sine term is determining what note you hear at 440.5 hertz. Okay? So that's, you're seeing both the amplitude and the period in that. In physics, this is called the phenomenon of beats, where I have two notes that are very, very close together, and because of constructive and destructive interference, they kind of tune in and tune out like this. Okay? And that comes out of, you know, this trig identity that we teach our students that they forget very quickly. All right, another application which is kind of fun is your basic telephone keypad. That's a 2, you know. Those sounds are constructed by 2 sine waves. The row is determined by this many hertz. The column is determined by that many hertz. And so if I play the 3, it's something at 697 hertz being added to something at 1477 hertz. And so you play those 2 things together, it sounds ugly because they're not in tune, but it's the familiar sounds we're comfortable with listening to somebody dial on the keyboard. So let's see, 3, 6, 8, let's see, what was the number? 9, 5, 5, 2. I think that was the number for dominoes at Stanford. That's one of those things you just never forget all through the rest of your life from all your undergrad years. All right, let's talk about adding a few more of these things together. So here I've got 440 hertz, sine of 800 pi t, and I'm adding these extra things on top. So this one here is 3 times as high. And I'm adding a small part of that. This one's 5 times as high. I'm adding a fraction of that. And I'm adding these extra frequencies. These higher frequencies that are multiples of 440 hertz. Those in music are called overtones, extra tones, that are in tune just at multiples of the base frequency. Now I've chosen these fractions on purpose. The pure middle A sounds like this. 1 note. Adding these 5 together sounds like this. A little bit more tinny. You can still hear the bass A in there, but you can hear the extra sounds on top. And for those of you that have played with synthesizers on a keyboard, a synthesizer basically is take your bass frequency and then start playing around with extra overtones that you can throw on top of it in order to make a distinctive sound.